Hello everyone. So today we are going to learn about op-amp, which stands for operational amplifiers. An op-amp is a high gain amplifier. Why high gain? Because it has a range of 10 to the power 5 to 10 to the power 6 amplifier, which is used to perform different variety of operations such as amplifications, addition, subtraction, differentiation, integration, etc. etc. So this is the basic structure of an op amp. These are the two input terminals. One is connected to the non-inverting side and one is connected to the inverting side. This is power supply, positive power supply, this is negative power supply. This is the output voltage. Today we are going to discuss about two of the most important variety of the operations, which is differentiator and integrator. So this is an integrator circuit. As shown in figure, this circuit produces the output voltage as the time integral of input voltage. This is an inverting op amp. It is connected to inverting side, in which feedback resistor RF, we usually in previous sections we used here RF, which was feedback resistor, but in this we will use CF, that is capacitor, which will be used in the feedback circuit. And op amp integrators are used in sweep generators, filters, and simulation studies in analog computers. Okay, let's derive the equation of this integrator circuit. Here we see that current is coming from this side and it is dividing at the node G as I1 and IF going to the feedback circuit. Applying KCL at node G, we get applying KCL at node G, we get I is equal to I1 plus IF. As we know from the previous sections that an ideal op amp an ideal op amp is something that has the I1 is equal to 0. That means input current will be 0. Why? Because the because of the input resistance which we apply here, which was infinite, and we know by this equation I is equal to V by R, that if this is infinite, this will be automatically 0. Okay, so now I1 is equal to 0. That means I is equal to IF. Here we will see that I, which is equal to Vs minus V2 by R, is equal to dq by dt. Q is equal to Cv. As we know, the value of capacitance. Okay, Vs minus V2 by R is equal to d by dt of CF into V. Now Vs minus V2 by R is equal to CF dV by dt. Keeping CF outside of the derivative function, we will get Vs minus V2 by R is equal to CF into, now see what we can write the V as. We can write the V as V2 minus V0. We can write here V as V2 minus V0 by dt. We can number this equation as 1. Now we know that by the concept of virtual ground, if this voltage is equal to 0, as this is earthed, so this voltage is equal to 0, so this will also be 0. That means V2 in this equation we have to put as 0, 0 and 0. So we will get Vs minus V2 by R is equal to 0, and here CF d by dt into minus V0. Now, so after deriving this equation, we will get dVs by dt is equal to CF, actually minus 1 by R CF into Vs. Here we will use V naught. Now we will get, on integrating both sides, integrating dV naught by dt into dt, we will keep the limit from 0 to t is equal to minus 1 by RCF integrating Vs dt 0 to t. Okay, we will get, after cutting these, we will get V naught is equal to minus 1 by RCF integration of Vs dt 0 to t. This is the final equation that we get of V naught, that means V output, after solving the integrator circuit. Hence we can see that the output voltage is proportional to the time integral of input voltage and minus 1 by CF into R, or R into CF is a constant. Okay, now we will move on to the differentiator circuit. This is a differentiator circuit. As shown in figure, this circuit produces output voltage as the, which is proportional to the time derivative of input voltage. Okay, this is an inverting op amp in which input resistance R is replaced by capacitor C. Okay, same thing here also we can do, applying KCL at node A. We'll get I You can see the direction of current here as well. I, here the feedback circuit IF, and here I1. We know this will be 0, so let's proceed. I is equal to I1 plus IF. So here in this circuit we can see I is equal to I1 plus IF after applying KCL. I is equal to IF. Why? Because of the input resistance of an ideal op-amp, which is infinity, and using equation I is equal to V by R, we get I is equal to 0. So after proceeding, we will see I is equal to dq by dt. By the definition, we all know IF is equal to V2 minus V0 upon RF. So after applying Q is equal to CV, we see d by dt into CV is equal to V2 minus V0 by RF. So we get here C d by dt Vs minus V2. V will be equal to Vs minus V2 for this capacitor. Okay, is equal to V2 minus V0 by RF. Numbering this equation as equation 1. By the concept of virtual ground, we all know the concept of virtual ground. If this is equal to 0, then this will also be equal to 0. Okay, now keeping the value of V2 here, so C d by dt Vs minus 0 is equal to 0 minus V0 by RF. C d by dt into Vs is equal to minus V0 by RF. So we get the final equation of the output voltage as the time derivative of the input voltage. So we will get V0 is equal to minus RF C into dVs by dt. Okay, this is all about the differentiator circuit and the integrator circuit. Thank you everyone.